and I work on basically improving the efficiency of ML systems. So in the past, that's been quantization. Last year and last summer, I worked on low precision training at Amazon, and that's what I'm presenting today. So
I think start sharing if you meant to share.
Yes, I will do that. So the title of this talk is Training LLMs with MXFP4. Kind of the overview is, we have these hardware accelerators like the B200 and MI355X, and they're starting to support these FP4 matrix multiplications. So we'd like to be able to take advantage of these when we have compute-bound workloads like training. So in this talk, I'll go over what low precision training is, and then I'll talk about the MXFP4 data type and how we figured out how to train with MXFP4. And as I mentioned before, this is based on a paper that we're publishing at AI Stats in about a month. It was done during an internship at Amazon. I highly recommend the team at Amazon. It's under Ida Wayne and Yansuk Park. If you're looking for an internship, feel free to reach out to them. I think they still have a few slots this year. So LLM training is really expensive. And here I'm talking about pre-training. But the training process is kind of fixed in the sense that almost all of these models are optimized with gradient-based optimization. So what that looks like is first you calculate some loss by doing a forward pass, and then you do a backward pass and you calculate your parameter gradients, and then you update your parameters based on these gradients and some optimizer statistics. So in Adam, you accumulate your first moment and your second moment, then you divide, and then that's your kind of adjusted learning rate times your gradient. So to do this, you have to obtain your gradients. And to do that, you have your forward pass to get your loss function and your output. And then you backprop and you take the derivative with respect to this loss for every single parameter. And this is expensive, and I'll show why later. But at large batch sizes, both of these operations are compute bound, which means that we can kind of accelerate them with these low precision data types. And pre-training, falls under a large batch size regime, so it's also compute bound. So if you wonder, all right, I have a compute bound regime, where do all the flops go? If you look at a large enough model, over 90% of the parameters and flops are in the decoder linear layers, which is nice because they're kind of well defined and relatively easy to work on. So a linear layer looks like this, y equals xwt or wx, and x is your activation vector. Its dimensions are batched by input dimension, usually n, and w is a matrix of m by n, which is m is the output features and n is the input features. Backprop is expensive. In fact, it's twice as expensive as the forward pass. You have to calculate two gradients. You have to calculate your error signal, which is this dldx, and that's the dldy that gets inputted to the previous operation. And that's dldy times w, which is b times m times n, which is about the same as xwt. And then you have dldw, which is the actual parameter gradient itself, and that's the thing you update the parameters with. And that's also expensive because now it's dldy transpose times x, which is like m times b times n, right? So in all three cases, they're about the same, and 2/3 of the flops are in the backprop. So this is a nice plot from this guy called Adam Casson, and he analyzed basically where all the flops went in a pretty standard transformer setup as, okay, let me, oh, sorry. As the parameters go up, and then also for a fixed sequence length of 4K. So the linear layers are basically this green bar, a salmon colored bar, and also this purple bar. And as you can see, as we go towards in the 100 billion parameter scale, basically almost all the flops are in the linear layers. And so it makes sense that if we can somehow accelerate the linear layers and leave everything else in its native precision, we can get a pretty good speed up and hopefully not sacrifice too much quality. So in low precision training, because we have all this compute, and it's basically like 3 map moles per layer that cause all this compute. The idea is that we can take advantage of these low precision operations on modern hardware, and we can accelerate these compute bound matrix multiplications. So there's a lot of low precision data types out there. Here's a chart. This speedup bar is kind of a lie on NVIDIA because FP32 uses CUDA cores and everything else uses tensor cores, and the tensor cores are just much faster than CUDA cores. But theoretically, the 16-bit numbers are twice as fast as the 32 data types. The 8-bit ones are 4 times faster, and the 4-bit ones are 8 times faster. There's a breakdown by type of sine, exponent, and mantissa. The exponent number tells you what the dynamic range of the data type is, so what the largest value relative to the lowest value is, or smallest value is. And the mantissa tells you how much precision there is, which is basically within a certain scale, which is determined by your exponent part, how much precision is there in that block. So due to how these data types are defined, they're actually kind of scale invariant with respect to SNR. This is a plot from another paper that I forgot to cite, but it shows this pretty clearly. So FP16 has 5 exponent bits and 10 mantissa bits, and it has the highest range and highest precision out of all these 3 data types. And also once you're inside of that range, you kind of have the same SNR, so it's scale invariant. FP4 has okay, so there's 2 FP8 data types, FP4 E4M3 and FP8 E5M2. E4M3 is 4 exponent and 3 mantissa, and E5M2 is 5-2. So FP8 E5M2 has the same dynamic range as FP16 because they have the same number of exponent bits, but obviously has much lower SNR and precision because it only has 2 mantissa bits instead of 10. And FP8 E4M3 has less range because it has fewer exponent bits, but higher precision because it has 1 more mantissa bit. So hopefully this chart kind of shows what the difference between each of these data types is and how you might choose one or another based on your input distribution. So to actually do low precision training, we do this thing called mixed precision training. And in mixed precision training, you have these high precision buffers and operands. And so these might be your parameters or gradients, and then you quantize them to a low precision data type for the matrix multiplication. But you keep your updates in high precision. And the reason you do this is so that you kind of don't lose the update precision as the numbers get smaller relative to the parameter size. So nice part about mixed precision is that it's implemented, basically everywhere, and also everybody uses it. So Llama, Gemma, most LLMs prior to this year were trained with 16-bit and FP32 mixed precision. So that means 16-bit matrix multiplications and FP32 buffers. And then some this year have come out with FP8, like DeepSeek, and I think Llama 4 as well. So, the funny thing is, like, we've had FP16 support since the V100 and BF16 since the A100, and we've had FP8 since the H100, and the H100 is like 3 years old now, but finally today we're starting to see FP8. So FP4 hardware support has started to trickle out, and hopefully we'll see a little smaller gap between FP4 hardware support and FP4 training. So the next part of this talk is going to be about the MXFP4 data type. It's kind of interesting because of the MX part. The FP4 part is just standard E2M1. And I'll explain why MX is useful later. So FP4 is fast, has high distortion as we expect. And the question we're trying to ask is, can we use these FP4 GEMMs, to accelerate training, because that's what they would do, but also do it without killing the model or making it worse on like a Pareto scaling frontier than say FP8. So the MXFP4 data type is nice because it has this MX scale. The official spec is it's an int8 scale shared over 32 FP4 elements. NVIDIA's version is called MVF4, and that 8-bit scale is FP8, but kind of the concept is the same. You have some sort of scale, and you have some sort of block that shares a scale, and the output is either, in the int8 case, it's 2 to the scale times your vector of numbers, and the NVIDIA case is just the scale times the numbers. So, this is, I guess, nice because it kind of does that fine-grained scaling that most quantization works do already, but it does it in hardware in a well-defined way. So, scaling lets us handle large dynamic range. The caveat is inside a block, if you have an outlier, then you're still going to get poor numerics because the scale of the block is determined by the largest magnitude element. And MX is also supported in hardware basically for free. So if we look at Blackwell spec sheet, you can see that for FP4 GEMMs, we can get about 9 petaflops. I don't remember if this is sparse or dense, but that doesn't really matter because all four are the same. FP8 is half, FP16 is a quarter, and FP32 is an eighth. And that tells you that the hardware can handle the scale and do the gem without kind of getting killed by performance, and that's nice. There's also, due to the way of how scaling is defined, there's also multiple different quantization algorithms that are all memory bound. And that's nice because that lets you do online activation, like activation quantization or gradient quantization. On the left here, I have the OCP one in their paper from like 2023. Let's assume you have an int8 scale. And on the right, I have half of NVIDIA's Cutlass Blonde that they put out like 2 months ago. And let's assume you have an MVF4 scale. But the thing on the right is just to show that, on the hardware we have today, the B200 and other Blackwell chips, we can actually do this in a reasonable amount of time. And like this quantization algorithm isn't going to kill you. So, MX is nice, but if you try to do it directly, it doesn't match 1632. So this is just using MXFP4 in the backwards pass, not even the forwards pass. And you can see there's about like a 1 to 2 perplexity gap on the GPT 1 billion and 6 billion, 7 billion scale. And that's basically not worth it, right? Because if we did FP4 or FP8, it'd be half the speed or a little more than half the speed. But it would match BF16 and you'd be better off just using that. So the question is there a way we can kind of close the gap between this orange curve and this blue curve? And the answer is yes, because I was too lazy to get rid of the other lines on the chart. Okay, so there's 2 reasons for this, at least 2 reasons that we identified. There's a lot of papers out there that identified other reasons as well. The first is that the MX quantization algorithm is biased. And that gives you biased gradient estimates, which can kind of kill your model optimization just because you have like consistently wrong gradient estimates. And the other is that you have these activation and gradient outliers that cause poor numerics. You can fix this in multiple ways, but the way we do it is specifically tuned towards making the MX quantization algorithm unbiased. So in our approach, first we only do the backwards pass in MXFP4. The forwards pass is, as we found, much harder to do in FP4. There is one paper that claims they can do it with kind of an EMA buffer. But then there's also that like low precision scaling loss paper that claims that as you reduce the precision in the forwards pass, you also kill performance. So we're leaving that kind of as an open question. Can we actually scale forwards pass FP4 up? So the first part that we do is we make MX quantization unbiased with stochastic rounding. And then the second part is we bound the variance of stochastic rounding with these random orthogonal transformations. I'll explain what that means later, but basically because stochastic rounding is stochastic, it adds variance, and that can also hurt optimization. So in order to minimize the variance, we can use these random orthogonal transformations and do them in kind of a memory bound and free way and improve the quality of the model. So if we do all this, we get about a 30% estimated end-to-end speedup versus FP8. This is FP8 forward pass for both, and then FP8 backwards versus MXFP4 backwards. This was actually tested using an int4 kernel on the A100 because we didn't have the B200. So, assuming a better kernel or something that NVIDIA has more modern support for, that number could probably be higher. And here's the chart, kind of a flow diagram of what we do. You get these gradients in, or you get these operands needed for the gradients in. You apply the random Hadamard transform, which is just the orthogonal transform that we used. Then you do stochastic rounding, and then you do the FP4 gem. So, all right, well, let's look at the MX quantization algorithm. So we claim that we make it unbiased, but why is it biased in the first place? If you look at this part here, line 1, essentially it scales an input so that the largest magnitude number is 8. This is bad and kind of a bug because the maximum representable value in FP4 is 6. And so it means anything that gets scaled to between 6 and 8 will just get clipped and rounded down, so it's guaranteed to be biased. We can kind of fix that for free. First, we fix the scaling by just scaling things by 3/4. So the largest thing gets scaled to 6. And then you do stochastic rounding, which actually is the thing that gives you unbiased rounding. So if you assume independent noise with your stochastic rounding, then these MXFP4 GEMMs, the output of the matrix multiplications become unbiased. And then we can assume nice things about the gradients and do hopefully nice theoretical analysis later. So for those that are unfamiliar with stochastic rounding, if I have a number C and I'm trying to round it to A or B, I either round C to A with probability, B minus C over B minus A, which is just the portion between C and B, or I round it to B with the portion between A and C. You can verify that, an expectation must become C, but in reality, C is either going to get rounded to A or rounded to B with some probability. Now, this is good because it tells you that in expectation, you're getting the original number out. But the bad part is it has variance, right? So in this example here, we have the variance of relative, it's like O of the order magnitude of B minus A. And it's just either you chose A or you chose B, and that's the variance. And you want to minimize this variance. And so traditionally, you only round to the points directly above or directly below you. But we introduced another way to take care of this. So, this is another thing. So you don't actually do this probability rounding thing in hardware. We do it with dithering. What dithering does is you sample a noise vector, and then you add it to your you add it to your input, and then you do nearest rounding. And I think somebody asked a question, or
yeah, I think no, I think it's just about the slides you put.
Oh, wait, so was there a question or not? I can't see. No.
No, I was just saying it was somebody asking for the slides later, so you can just go ahead.
Oh yeah, sure. Okay. Yes. All right, so you might ask, what is the cost of stochastic rounding? Thankfully, Amazon has a chip that does stochastic rounding, and when we wrote the paper, it was the only chip that does stochastic rounding, but as we found out, the B200 also does stochastic rounding, so now there's two. When we benchmarked a gem with stochastic rounding turned on, for a really large matrix, it was less than 2% overhead. For like a smaller matrix, it's about 5% overhead, but that's pretty reasonable because the delta between FP4 and FP8 is 2x, and 2% is a lot smaller than 2x. So as we found out by reading the PTX, Blackwell also supports stochastic rounding. It's kind of weird because you have to put in the actual noise vector itself, so I'm not sure how they expect you to generate that. I assume you could use like an LCG or something, and also NVIDIA didn't really announce this. But in theory, you can do stochastic rounding on the B200 now, and it was only introduced in the B200, which is SM100A. So that's kind of nice. Right. So you can do stochastic rounding. This is algorithm 2. This is our modified version. Line 4 does the scaling by 3/4, and line 5 does the stochastic rounding. And if you do this by itself, it already gives you, unbiased gradient estimates, and technically you could just go on and use this. But we also kind of want to bound the variance of, stochastic rounding. So if you look at this plot on the right, this is a distribution with two outliers, one at the beginning and one at the end. And this is MX quantization, and it's nearest rounding, but that's not the part that matters. So you can see that for most of the numbers, they get either rounded up or rounded down, but to the two smallest values in the representable data type. And that's roughly the variance of the rounding for these numbers if you did stochastic rounding. And the variance is roughly the magnitude of the numbers themselves. And that's just bad because, basically you're just getting noise for most of the entries that are not outliers in this matrix. And so, why is this a problem? Well, if we look at when we calculate the gradients, DLDX is dependent on the error signal, which has outliers in it, and also DLDY is dependent on both the error signal and the activations, both of which have outliers in them as well. And so if we have, outliers and we get high variance gradient estimates, and we can also get poor convergence, which is bad. So how can we fix this? Well, first we look at, all right, how do we characterize the variance of stochastic rounding? We show that it's O of the L infinity norm of a matrix if you do MX quantization. That kind of makes sense. It just tells you, my variance is roughly at the scale of the largest element in this matrix, which is, it's kind of an output or it's an artifact of the scaling of MX. All right. And then you ask, all right, well, can I bound this somehow by just reducing the largest element in this matrix for free? And the answer is yes, kind of for free with this thing called the random Hadamard transform. So you've probably heard of lists if you work in quantization because like 10 million papers use it now. But here we use it in a slightly different way, but it's the same transformation. So the random Hadamard transform is just an instantiation of a random orthogonal transformation. It's just one type of random orthogonal transformation. And it's defined by doing x gets hsx, where s is a random sign vector and h is a Hadamard matrix. So the randomness comes from s, and it's also really easy to randomize because you just sample random sign vector. The Hadamard matrix is this recursively defined matrix that's orthogonal. And it's nice because of the recursive definition, it admits O of n log n matrix vector multiplication. When we introduced the RHT for quantization in QuipSharp, there were basically no good RHT kernels. I think TreeDAO had one, but now Facebook has one called Cohere, and it's better than Tree's kernel, or at least faster on their benchmarks. And so it's what you're able to do is fast now. It's not just fast in theory, it's also fast on hardware. But that's all nice. The part we care about is that if you apply the random Hadamard transform, the largest element, or basically all elements, follow a roughly sub-Gaussian tail decay. And empirically, it makes it effectively IID Gaussian. So if I apply the Hadamard transform to some vector, it basically whitens it and becomes Gaussian, and that lets me bound the largest element by just reducing its magnitude for free. And then because it's orthogonal, I can invert it in the other matrix multiplication. So here, this is just describing how we do matrix multiplication. If I'm trying to do A transpose B, if I do HSA transpose HSB, then this is up to numerical precision the same thing because the H, ST, HT, HS cancels out because it's orthogonal. And if I quantize HSAT and then I multiply that by a quantized version of HSB, I get roughly ATB in the end. The second line is nice because when I do the quantization, HSA and HSB have bounded tail distributions, which means I can bound the variance in stochastic rounding. So this is the actual theorem that we have. Without the RHT, this is what we had like 3 slides ago. With the RHT, now your linear dependence in log size becomes a log dependence, and in exchange you trade it for the L2 norm instead of the L infinity norm. If you have outliers, the L2 norm and the L infinity norm are actually roughly the same, and that's conveniently where we actually would care about the RHT. So, you can plot this empirically, essentially with the RHT, which is these solid lines, versus without, you get much lower variance and much better scaling with variance as your block size increases. So finally, I'm going to talk about some practical considerations about applying the RHT. So if you apply the full RHT, then you kind of incur this really expensive cross-device I/O. So when you calculate DLDW, you're reducing along the batch dimension. So DLDY is B times M. So this matrix multiplication is M times B times a B times N matrix, and B is your data dimension. That's what you're reducing across. If you do the Hadamard transpose there, in any sort of data parallel setting, you're doing the Hadamard across multiple GPUs, which is just a terrible idea. And the other thing is that the RHT is compute bound even if you do the unlog n matrix vector multiplication. So that could be fine if you're willing to pay that cost, but at the same time, training's already compute bound, and it's generally not a good idea to add more compute bound things. So instead, we take advantage of MX's scaling. Recall that MX scales for every 32 elements. And if we instead apply a small block RHT as a dense matrix multiplication, where the block size is like less than 256, then it becomes memory bound. And even though it's 256 and you only get that concentration per block at 256, that's fine because MX's scaling will take care of that and the rest of the between block scales for you. So what I mean by all this is if you look at this diagram, if we apply the RHT as a dense matrix multiplication, the small dense matrix multiplication, then we can transform A and B in essentially a memory bound way where it's bound in the memory of A and B. And then you get the matrix multiplication AB basically for the cost of an FP4 gem. So, if you look at this and you think about it and you're like, why the RHT? Because, if you're just doing a dense matrix multiplication, you can use any random orthogonal matrix. The only reason we do it is because it's fast to randomize. You can, do that with a random sign vector, but technically you could use any random orthogonal matrix, including one that you've kind of tuned and picked. And then you could also randomize it by adding a sign vector as well, because sign vectors are orthogonal. So if we look at everything all together, this is our entire method and algorithm too. First, you apply the RHT over a small number of blocks, which is this section here. This is in torch notation. You do a view and then you do the multiplication, but it's essentially what I drew out on the last slide. Then you use stochastic rounding to get an unbiased, estimate of your inputs, and you quantize in the Hadamard space. So that's this part. And then you do the gem, which is also this part. And if you're using algorithm 3, which is the stochastic rounding version, then you'd scale up because you scale down by 3/4. So you'd scale up by 16/9 to take care of that. We evaluated our method on a variety of pre-training experiments, basically on these smaller scale, up to 7 billion parameter GPT models for about 20 billion to 40 billion tokens from Wikipedia. And we also did a larger run for 1B for 200 billion tokens. And in our experiments, we used a Hadamard group size of 64, and we used a Microsoft microscaling library for MX emulation. At the time, we didn't have the B200, but if we have one now, we'd probably just use that instead. But at least here, we know that microscaling is supposedly bit accurate. And over almost all of our experiments, we saw less than a 0.1 validation perplexity gap to 1632 mixed precision, which is usually like kind of the error threshold for what you think is like relatively lossless. So this is GPT 345M for 33 billion tokens. The orange line is FP4, just like naive FP4 out of the box for the backwards pass. And if you add the Hadamard transform, stochastic rounding, or both, you can get very close to BF16, which is good. This is GPT 1.3b. Again, the same story. If you do what we propose, which is the red line, you can get essentially the BF16 curve. If you do the like either half of the things we propose, it also is pretty close, but if you zoom in, it's a little worse. But if you don't do anything, it's just like not worth doing. This is GPT 6.7b, also same story. We canceled the FP4 run because training GPT 7b is expensive, and it was kind of obvious that it wouldn't match. But it does scale up to slightly larger models. And finally, here's the big run that I think is the most interesting. So if you just do the Hadamard transform without stochastic rounding, so here you get a biased gradient, but it is, it is concentrated, so you get relatively good numerics. At the end, you see there is a gap between only doing the Hadamard and BF16. Whereas if you do the Hadamard BF16 and the Hadamard the Hadamard FP4 and stochastic rounding to get an unbiased gradient estimate, and even at 210 billion tokens, you're matching BF16. So that kind of tells you do need these unbiased gradients, maybe not at the 20 billion parameter scale, but definitely at the 100 billion or trillion parameter scale. And then finally, we also tested with FP8 forward passes. We have these FP8 training algorithms. The question is, if we did an FP8 forward pass an FP4 backwards pass, would that, kill quality, or is our thing compatible with that as well? And, it does work, which is good. And it works for 1.3 and 6.7. And then we also tried some fine tuning. So we took our GPT 6.7 billion parameter model, the one trained with VF16 FP4, and we did Tulu V2. For the actual fine tuning part, we just used VF16 for forwards and backwards. So this is just evaluating the quality of the model. Both before and after, both models got about the same downstream zero shot performance. They're all kind of terrible because they've only been trained on 20 billion tokens, but they are, about the same, which is what you would expect for models that are similar to each other. And then finally, we did some throughput estimates. We estimated the FP4 throughput by looking at INT4 on an A100. It has the same speedup versus VF16, which is what we care about. And if we look at the end-to-end tokens per second, this is for Llama's 7dB 1 decoder layer. You get very little performance hit from doing the RHT. And it is essentially memory bound up to like about 256, right? So without the RHT, INT4 is about 134,000 tokens a second. If you add the RHT for like smaller group sizes, it goes down to about 120,000 tokens a second. But if you increase to like a 1K block size, if you do a dense matrix multiplication, then it drops down like 110. The Facebook had a core kernel, which is the last column on the side, is actually surprisingly good. I know Tree's kernel does not get 120,000 tokens a second, but yeah, if you do the unlog-in version, it's actually not that far off of the memory-bound version. So the takeaways from all this are that, we can train your lossless models with MXFP4, but by using it in the backwards pass, it's much harder to do it in the forwards pass, but there are some works that are starting to come out and doing that. You can do your gradient computation relatively low precision, as long as you have unbiased gradients at the end. So if you can get unbiased gradients and also bound the variance, then you can also get more accurate updates, and it doesn't really matter what precision you do the computation in. So that's the end of my slides. There's a few things we wanted to do that we didn't get to do. One is just do it on the actual hardware, which didn't exist when we wrote the paper, but does now. And then there's also testing at much larger scales, like larger models or for trillions of parameters or trillions of tokens, which we also didn't get a chance to do. But hopefully somebody with more money than us can do that. But yeah, that's those are my slides. That's my talk, and thank you all for coming.